there is a way to determine if a function is even or odd based on the equation for a function, and that's where we're going to pick up with new material. So this is very similar to what we were doing back in chapter 2 with the 3 different types of symmetries, x-axis, y-axis, and origin. Of course, we're only focusing on y-axis and origin. We're not going to be worried about functions that have x-axis symmetry because those graphs actually are not graphs of functions, so they get left out. But you may recall that when we were testing an equation for symmetry, we had to plug some negative variables into the equation. And so you can kind of use that as like a frame of reference for when we establish whether or not a function is even or odd algebraically. To see if a function is even, what we do is we plug negative x into the function f of x, and then we simplify. And here's what we're looking for after we simplify. If the simplified version or the simplification yields the original function, then the function is even. So if we plug negative x into f of x and it looks like nothing has changed after we simplify, then that would be an example of an even function. To see if a function is odd, we again plug negative x into the function and simplify. And this time, if the simplification yields the opposite of the original function, then the function is odd. So I'm going to show you a way of looking at all the different possibilities that we would get when trying to see if a function is even, odd, or neither. And I'm going to do this in kind of like a tabular format. I'm going to kind of set up a table here. And the table is going to have 3 columns and 2 rows. The first column, I'm going to head it with f of x. The second column is going to be a workspace for f of negative x. And then the third column is going to be a workspace for the opposite of the original function, so negative f of x. Now, in this first column, the column for f of x, let's just jot down the original version of the function, so 7x squared plus 1. All right, and that's really all we're going to do in that column. In the second column, if you look at the notation, it looks like we need to plug negative x into our function. And so we're going to do just that. Where it says x squared, in this expression 7x squared plus 1, we're going to replace that x with negative x. So 7 times negative x squared plus 1. Which, by the way, how does this simplify? Negative x quantity squared. What would that turn into? X squared, yep. So this is really 7 times x squared plus 1. And I'll just remove parentheses to get 7x squared plus 1. Now for the last column, the negative is in front of the function notation. All this simply means is that we're going to take the number negative 1 and distribute it to the original version of f of x. So let's do just that. We end up getting negative 7x squared minus 1. Now, do any of these results match the original version of the function? Or do we have any matches within the table? Okay, we have 7x squared plus 1, and that matches up with the result from the second column. You guys see that? So because the result of f of x matches with the result of f of negative x, what it means for us is that f of negative x is equal to f of x. Now, if you want, go back to that very first page of this note packet. Which definition does this line up with? F of negative x equals f of x. Even, yep. So this is actually the definition for an even function. So what this would imply is that our function f of x is even. And check this out. If you were to sketch this graph on the graphing calculator, you would find that this graph is kind of like a narrow U-shaped curve. It's a parabola, maybe something like that. And this would be a graph having y-axis symmetry. And so because this graph would have y-axis symmetry, we would know that it's an even function. So we could actually verify our algebra here by looking at the graph on the graphing calculator. Okay, so I won't do all of that, but I just kind of want to make a note of it that you do kind of have a way of establishing your work using the graphing calculator. You guys have any questions about this example? All right, let's try this again with the function in part B. We'll make our little table. First column for f of x, second column for f of negative x, and then third column for the opposite of f of x. So for this first column, just going to jot down the original version of the function, x cubed plus x. For the second column, we're going to change all of our x's to negative x. So there are two spots in the equation in which we'll do that with. So negative x quantity cubed plus negative x. Now, when we raise a negative expression to an odd power, it remains odd. I'm sorry, it remains negative. So there are three negatives getting multiplied together here, and the end result would be negative, in particular, negative x cubed. And then I'm just going to rewrite the last part of the expression with direct subtraction. So we get negative x cubed minus x. For the third column, the opposite of f of x asks us to distribute negative 1 to the expression x cubed plus x. And when you distribute it, you're going to get negative x cubed minus x. Now, do any of the expressions within the table match each other? About negative x cubed minus x, negative x cubed minus x. Yep. So the results from these two columns match each other. And because of that, it demonstrates that f of negative x is equal to the opposite of f of x. And based on page 1, this would mean that our function is odd. Okay? So I'm going to have you try it out. with the function in part C, I'll flesh out kind of an empty table here. And after giving you a few minutes to work on it, I'll include my details and we'll see how we did. Okay, so go ahead and see if you can determine if this is an even, odd, or neither function. And we'll go from there. So these are what I'm getting. It's my simplified expressions. Of course, nothing really to do with the first column, but when you plug negative x into the function f of x, okay, it just goes right here. That will make the term 4x equivalent to negative 4x, and then the plus 5. And then, of course, with negative f of x for our last column, we would distribute negative 1 to both these terms, giving us negative 4x minus 5. Now, with that said, are there any matches within the table? No matches. So I'm just going to make a note of that. No matches, which means that it is definitely a neither function. You got it. And if you were to graph it, sorry to not mention that with part B, but if you were to graph the functions in parts B or C, part B, you would be able to establish that it has origin symmetry with some reflections, whereas the graph in part C, you would notice that it doesn't have y-axis symmetry and it doesn't have origin symmetry. So when it doesn't have either of those two symmetries, you're working with a neither function. Okay, and that's it for the even and odd function part of this note packet. Do you guys have any questions about this particular topic? Okay. Well, we'll now get into the behaviors of functions. This one isn't necessarily a behavior, but it does give way to changes of behaviors in functions, particularly their graphs. Now, we'll start things out with a handful of definitions here, and then we'll get to some visual representations of these with a couple of examples. But with that second problem of the written work, one of those parts deals with this topic. And the topic here is on maximum and minimum values of a graph. And, in plain old English, when we're trying to look at these values of a graph, we can identify them by looking at the high points and the low points of a graph. So we know by now that a graph can, look like a variety of things. A lot of our graphs have like these hills and valleys to them. The graph kind of wiggles a little bit. And those points that are sitting on top of the hill or at the very bottom of the valley are what the maximum and minimum terminology refer to. And in the old days, these were often called the extrema of a graph. We typically call them maximums and minimums, though, versus extrema. Now, let's get to the definitions, and I'll give you an important couple of tips, and then it's really not that difficult of a topic here. I think sorting out the definitions could be the most difficult part, but I'm sure you guys will catch on fast. So a y value that is larger than the surrounding y values, and what I'm referring to here are y values of points on the graph. If we have a y value that is larger than the surrounding y values, that y value would be called a local minimum, sometimes alternatively referred to as a relative maximum. I think I said minimum at first. So a y value that is larger than the surrounding y values is called a local maximum. A y value that is larger than all of the y values is called an absolute maximum, aka a global maximum. A y value that is smaller than the surrounding y values is called a local minimum, or alternatively, relative minimum. And then a y value that is smaller than all of the y values is called an absolute minimum, or global minimum. Now, when we are analyzing a graph for these points, and you get a problem asking you for what the maximum or what the minimum is, you're always going to report the value of the y-coordinate. Sometimes, though, they'll also ask you when or where this maximum value occurs. So any part of a question that's asking you for when or where a maximum or minimum occurs, that's going to be given by the x-coordinate. And in a lot of cases, you can report both of these values at the same time just by using the ordered pair associated with the high or low point. Now, one thing that I like to do with maximum and minimum problems, if we're reporting them as ordered pairs, I like to indicate that the value of x tells us where this maximum or minimum is at relative to the x-axis, and then the value of y is the official value of that maximum or minimum. So let's tie all this in together with a couple of graphs. Our first example wants us to find the absolute maximum and the absolute minimum if they exist. And here we have a graph of a function. It starts at 0, 2, and ends at 5, 0. Now, they want us to find the absolute of each of these. So we're looking for a highest point on the graph, and we're also looking for the lowest point on the graph. Anybody want to help me out with letting me know what the highest point on this graph is? 4, 4, yeah. So this point right here is the highest point of the entire graph. This would be referred to as the absolute maximum. I'll say absolute max. What would be the lowest point on this graph? 5, 0. that would be the absolute min, short for minimum. Now, there's another low point on this graph, 1, 1, but because this isn't the lowest point on the graph, we could not call 1, 1 an absolute minimum. The best we could classify that point would be as a local minimum, or local min for short. Now here's where it can get a little bit dicey, and I'm not trying to complicate this for you. I just want to help you differentiate the terminology. 1, 1 is not an absolute minimum because it's not the lowest point on the graph. But referring to the absolute maximum, 4, 4, that is the highest point on the graph, but it also is the largest y value relative to the points that are near this point. So like points that are to the left of 4, 4, points that are to the right of 4, 4, they all have y values that are smaller than the y value of 4. So 4, 4 is not only an absolute max, but it's also a local max. And that's because 4, 4 has a y value that's larger than the surrounding y values. What I mean by that is its y value of 4 is larger than the y values of points that are on either side of it. The absolute minimum of 5, 0, that cannot be classified as both an absolute and a local minimum. And the reason for that is because 5, 0 doesn't have any of those surrounding points. It's got points to the left of it, but there are no points to the right of it. And so anytime that you have a point like this, which is called the endpoint, the only possibility for an endpoint is that it's either an absolute minimum or absolute maximum, or in some cases it might not be either of those. So for example, if you look at the point 0, 2, that looks like a high point on the graph. It's not the highest point, so 0, 2 would not be the absolute maximum, but it wouldn't be a local maximum either because it only has points to the right of it and not to the left of it. So 0, 2 would be nothing. I'm going to say nada. Okay. So with that said, we're going to fill some things out here. Absolute maximum at. Okay, so that's going to be the x coordinate of our absolute maximum. I'm going to write x equals 4. The actual value of the maximum is y equals 4. Okay, so it's at x equals 4 and has a y value of 4. And if you wanted to bundle these up as an ordered pair, you're more than welcome to do so. And we have an absolute minimum. The absolute minimum is at x equals 5, and it has a y value of 0. So 5, 0. With this example, they want us to see what numbers, and what they mean by that are any values of x for which the function has a local maximum. So they want local this time. They would also like to know what the value or values of those local maximums are. And then they want us to see if this graph has any local minimums in addition to what those values are. Now, notice that they're not asking for absolute maximum or absolute minimum. Does anybody have a suspicion as to why they're not asking for absolutes this time, like absolute maximum or absolute minimum, just based on how this graph looks? Yeah, pretty much right on track with that. If you look at the ends of the graph, they have arrowheads. And that implies that the graph, the ends of the graph continue on in these directions forever and ever. So like this part of the graph keeps going up forever and ever, and this part of the graph keeps going down. So technically there is no highest point on the graph because you could always find one higher than it. Likewise, there's no lowest point on the graph because you could always find a point that's lower than it on the graph. So there are no absolute maximums or minimums because of how these ends are situated. But locally, okay, there are certain sections of the graph where we do have a high point and a low point. For instance, in quadrant 1, pi over 2 comma 1, that's not the highest point on the graph, but if we just focus on this little section of the graph that's in quadrant 1, this would be the highest point. Okay, so this would be considered a local max. And this happens at the x value of pi over 2. Or in the words of Cartman from South Park, pi over 2. And the value would be y equals 1. In ordered pair format, that would be pi over 2 comma 1. Is there a low point on the graph? And if so, where would we find that point at? So right down here in quadrant 3, we have a low point on the graph. It's not the lowest point, not the lowest point of all right, but it is a low point nonetheless. And because of that, we would classify that as a local minimum, or local min for short. So that happens at the x value of negative pi over 2, and the actual value of the local minimum is negative 1. Okay? Is this making sense so far? All right. So here's where we get to the official quote-unquote behavior of a graph. We'll introduce some definitions, which allow us to work with this concept. And basically, you can get a little interactive with the graphs when trying to answer questions related to this topic, in the sense that you could literally put your finger on a graph and trace it. And with some graphs, you'll find that your finger goes up on the page, or maybe it goes down, or maybe it just goes straight from left to right. But those sections of graphs that go up or down or stay flat, they are important for us, and we're going to learn how to identify those as well as best describe them. And so let me go ahead and introduce what those sections of the graphs are officially called. Section of the graph that is going up as you trace your finger along it, going from left to right, would be a part of the graph that is increasing. So increasing behavior is when a graph is going up from left to right. So essentially your finger will kind of go in this direction. Decreasing would be when a graph is going down from left to right. So if you were to trace your finger along a graph, and let's say your finger goes in this direction for a little bit, then that would be a part of the graph that's decreasing. A constant part of a graph is when the graph is neither increasing or decreasing as you go from left to right. And so basically your finger would just go directly to the right without going up or down any. Now, when you identify those pieces, you use those pieces in conjunction with the x-axis to form your answers. And so in this box here, it says we use sections of the x-axis when answering increasing, decreasing, or constant problems. And I know it's kind of the elephant in the room here. With this first example, we're missing a graph, and that was totally an oversight on my behalf. I actually had intended to use the graph at the bottom of page 4, but I came up with a better idea. I'm going to have us construct a graph that's different from this one. That way we get a better variety of the different behaviors a graph can have. So if you wouldn't mind following along with me, let's draw a coordinate plane. And we're going to plot a few points together. The first point that I'd like to plot is -5, 3. Okay, so if you could plot that, that'd be great. The next point I'd like to plot is -2, -4. The next one is going to be 3, 2. And I think that's all I want to plot. And here's how I'd like us to connect these points. I'm going to start in quadrant 3 and just draw a line segment going up from -infinity to -5, 3. Then I'm going to connect the points -5, 3 and -2, -4. And then I'm going to connect -2, -4 with 3, 2, just like that. And then beyond the point 3, 2, I'd like us to just indicate kind of like a flat part of the graph that continues on in this direction. And I'm also going to put a little arrowhead at the very start of our graph. So what I'd like us to do is focus on a starting point at this very left end of the graph. And what I mean by that is if you're able to put your finger on that part of the graph and trace the graph along with me, we'll determine whether or not these pieces are going up, down, or just staying flat. So if we start here where I have the little highlighting on the graph, and if we trace along the graph, we would find that our finger goes up on the page. And so to indicate that our finger would do just that, I'm going to put some arrowheads going along the graph like so. And because this would be a section of the graph that goes up as you trace it out with your finger, this would be a part of the graph that's increasing. So I'll say INC for short. Then you get to what appears to be an absolute maximum, -5, 3. And once you move past that point, what is your finger doing on the page? Is it going up still? Is it going flat? Or is it going down? Be going down, yeah. So this next section of the graph, because your finger would go down on the paper as you trace it out, this would be a section of the graph that's decreasing until you reach the point -2, -4, which appears to be a local minimum. What happens as you go beyond the point -2, -4? You get a section of the graph that increases again until you get to this point 3, 2. What happens after you go beyond the point 3, 2? Yes, exactly. So, all things considered, if you were to continue tracing your finger along the graph past 3, 2, your finger wouldn't go up or down. It would just kind of stay flat. So this would be a section of the graph that's representative of a constant part. And just for sake of completion, that would be an increasing section of the graph. And so we have a variety of behaviors here. The graph first starts out by increasing, reaches -5, 3, then decreases for a little while to get to -2, -4, and then increases to get to 3, 2, and then stays flat, or in other words, stays constant from there on out. Now, keep in mind that we have to use sections of the x-axis when answering these types of problems. And in this example, the very first thing they want us to do is identify where the graph is increasing. And by that, what we mean is, where's this graph increasing relative to the x-axis? Now, remember, our graph started out by increasing, and the x values that correspond to the first part of the graph that's increasing go from -infinity all the way up to what tick mark? Well, keep in mind that after the point -5, 3, the graph decreases. So this part of the x-axis where the graph is first increasing goes from -infinity all the way up to this x value of -5. And then where does this graph pick back up for increasing? Like, between what x values is the second part of the graph increasing? -2, yep. All the way up until you get to the x value of 3. So these two sections of the x-axis are what we're going to use to answer this part of the problem. It's increasing on the x values of -infinity to -5. I'm going to use parentheses on -5, but I'll make a comment about that in just a second. And it's also increasing between the x values of -2 and 3. And much like with interval notation, since we have two different intervals here, we're going to union them together. Now, I do want to mention that it's easy to confuse some of these answers with ordered pairs, such as -2, 3. That looks like an ordered pair, even though it's an interval of the x-axis. So sometimes what the author will do is use brackets on anything that's not infinity. Let's see if I have some room for that. So you might see this, say, in my math lab or the textbook as -infinity, -5 bracket, union, bracket, -2, 3 bracket. Now, I'll let you know that courses, beyond ours, say like calculus, whichever one, it actually starts in Calc 1, they typically use parentheses on these values of x where the behavior changes. Okay, so I will usually write the answer using parentheses on everything, but I do want to kind of give you a heads up that sometimes my math lab will indicate these answers using brackets on anything that's not infinity. All right, so if it comes to that point and you're confused as how to express your answer, just reach out to me and I'll definitely help clarify that for you. But I'll usually use parentheses on everything. Okay. Now this graph is decreasing between the x values of -5 and -2. And that's really the only section of the graph that's decreasing. So, for the second part, where it asks for decreasing, we'll just write -5, -2, and slap some parentheses on both those numbers. Anybody want to offer the interval of the x-axis where the graph is constant? Yep, 3 to infinity. Very good. So 3, parentheses, infinity, parentheses. Okay. Well, before we break, I'd like you folks to take a couple minutes to see if you can identify the intervals of the x-axis where the second graph is increasing, decreasing, or constant. Okay, so I'll give you a couple minutes to work on that. And then during the break, I'll post my answer and we can go over it once we return. All right, so go ahead and take the next couple minutes to see where the graph's increasing, decreasing, or constant. And we'll go from there. All right, folks, you're welcome to a 5-minute break. While that's happening, I'm going to go ahead and jot down my solution, and when we come back, I'll go over any questions that you might have. All right, so I'll see you guys in about 5 minutes. Alrighty, welcome back, folks. Can you guys hear me okay? All right, thank you. So there are two sections where the graph is increasing. One part's from the x values of -1 to 1, next part from 3 to infinity. And the other two parts of the graph are decreasing. First part goes from -infinity to -1, and then the second part is between the x values of 1 and 3. And there are no parts of this graph that are flat, so that would not be applicable. So I typically just put NA for that. Did you guys come up with similar results? Y'all rock stars. Okay, let's move on to our last example of this section. We will need the graphing calculator for it, so if you need a moment to grab your graphing calculators, go for it. I gotta get mine ready actually. There we go. All right. So the graphing calculator can be used to help you approximate where maximums and minimums are at on the graph of a function. And once you find those maximum and minimums, if it has any, you would be able to establish where a graph is increasing, decreasing, or constant based on the x-coordinates of those extrema, or maximums and minimums. And so that's the skill I'd like to teach you guys with this example. It says, use a graphing utility to sketch f of x equals x cubed minus 4x plus 1. Now, the way we enter this into the graphing calculator is much like before. Keep in mind f of x is function notation for the variable y, so we would be able to type this into the y1 row of our graphing calculator as x cubed minus 4x plus 1. All right, so let's start out with that. So we'll go to y equals x caret key 3. And we'll get back down on the ground. Big minus sign here, minus 4x and plus 1. Let's hit zoom, select option 6. All right, how does this look to you folks? Getting a similar graph? All right. Now, you may remember the menu for the zero and intersect feature. We're actually going to use that menu still for this part, but we're going to select two different options because we're looking for the different parts of the graph. We're not interested in intercepts when finding the max or the min, although it is possible for those to land on the x-axis. It looks like we have a maximum in quadrant 2 and a minimum in quadrant 4. There would be no absolute maximum nor absolute minimum because the ends of the graph appear to be going forever in those directions. So just locals here. Let's start with the local max that's in quadrant 2. We're going to press second trace. And if we scroll down to option 4, where it says maximum, this is going to be used to help us find that ordered pair for the point in quadrant 2. So let's press enter. And we've got to be careful here. It will ask you for left bound and right bound and a guess. And we still have to provide answers to those when finding a maximum or minimum. But I don't want us to confuse this with intercepts. Okay, so remember, we're trying to find a high point here. And this high point's in quadrant 2. Now, left bound in this situation is going to be an area on the graph that's to the left of this high point. So my recommendation would be to scroll over to roughly this area of the graph. that's to the left of the high point. That would be a good left bound. Go ahead and press enter. And a right bound, we're going to move the cursor on the other side of this hill, if you will. Okay, so maybe somewhere on this section of the graph, you can go ahead and press enter. And we have two arrowheads facing each other with a little gap between them. That's a good sign. What we want to do now is move this point near the local maximum. Okay, go ahead and press enter. And I'm getting roughly negative 1.15 and 4.08. Do I have confirmation on those values? All right, cool. Anybody getting something different or an error or anything like that that I can help out with? All right, so let's hunt down the local minimum that's in quadrant 4. We'll hit second trace again, but this time we're going to use option 3. Select option 3. And a left bound is going to be to the left of this low point, so maybe somewhere right here on the graph. Let's scooch it over. Okay, so I'm a little close to the local minimum, but I think that's still going to work out for us. Let's go ahead and press enter. And then we'll go to the other side of this point. Maybe somewhere right here on the graph. That's to the right of this local minimum. Press enter. And our guess, we'll move the cursor close to that low point as best as possible. We'll press enter. And this one appears to be at 1.15, negative 2.08-ish. How's that sound to you guys? Rock on. Anybody need me to repeat any of those steps? Okay. So I'm first going to sketch the graph in this blank coordinate plane. And I'll include an indication of the local maximum. This was at roughly negative 1.15, comma 4.08. And that'll actually be our answer for part A. It says find the local maximum. So let's write it out as an ordered pair, negative 1.15, comma 4.08. And although not necessary, it will be helpful later on. Negative 1.15 is where this high point is at relative to the x-axis, and then 4.08 would be the actual value of the maximum. And then our low point in quadrant 4 was at positive 1.15, comma negative 2.08. And that's going to be our answer to part B. And again, not necessary, but helpful later on. 1.15 is where this minimum is at relative to the x-axis, and then the value of it is roughly negative 2.08. Now we have a couple more parts. We want to know where the function is increasing and where it's decreasing. What's going to be helpful for us on this regard is making tick marks on the x-axis where we have these high and low points. For example, our local maximum has an x-coordinate of negative 1.15. So what I'm going to do is right underneath this point, I'll put a tick mark and write negative 1.15. Our local minimum has an x-coordinate of positive 1.15. So I'm going to go up to the x-axis, put a tick mark there, and write down positive 1.15. Now let's start with our fingers right here on the graph. As we trace it from left to right, what kind of behavior is happening first on this graph? Is it increasing, decreasing, or constant? Increasing. And then once we reach the local maximum, the graph begins to do what? Decrease. Okay? And then once we reach this local minimum, the graph continues on the rest of the way with increasing. You got it. So for part C, they want us to provide the intervals of the x-axis for which the graph is increasing. Go ahead and see if you can whip up the interval notation for the two sections of the x-axis. And then for part D, you'll include the part of the x-axis where the graph is decreasing. All right, so I'll give you the next minute or so to work out those intervals as well as the interval notation, and we'll go over it. All right, so for part C, the first section of the x-axis goes from negative infinity to negative 1.15, and the second section goes from 1.15 to positive infinity. And then for part D, it's from negative 1.15 to 1.15, and that's it. So let me go ahead and whip up the interval notations, and we'll go over any questions you have. Okay, you have any questions about our answers to part C and D? So I'm not certain as to why the author uses brackets for increasing and decreasing answers, but I have a hunch that it has something to do with answers that resemble those for part D, negative 1.15 comma 1.15. With the parentheses on each of these, it kind of looks like an ordered pair, doesn't it? Like a point on the graph. So if we were to write this instead as bracket negative 1.15 comma 1.15, maybe it might be easier to not confuse our answer with an ordered pair if we use brackets instead. So my hunch is that the author uses brackets probably for cases like this where the answer looks like an ordered pair. I think with something like part C, when we involve infinities and things like that, as well as the union symbol, it's not really, as confusing because there's more interval notation involved here. But anyway, that's just an aside.